Okay, last time we introduced the concepts involving rotational energy and developed some formulas that we can use, specifically a formula that we can use to calculate the kinetic energy of an object in rotation, and then also formulas for the moment of inertia, which is essential for calculating the kinetic energy of an object in rotation. So I want to quickly just recap that, and then we'll get into a new concept that will give us another way to think about objects in rotation. All right, so our primary goal is to be able to explain an object that's both translating and rotating simultaneously. So in general, objects can be doing both at the same time, and so their energy is tied up into both those modes of movement, translating, or moving kind of in a linear pattern, or even in projectile motion, but also rotation around their center of mass or about some fixed rotation axis. So the first thing that we did was to imagine taking an object that is rotating and breaking it up into tiny little chunks, and for each chunk thinking about how much kinetic energy that little chunk of matter has. Add them all up and you get this formula for what the kinetic energy of rotation would be, which involves this quantity, and this quantity is essentially the mass distribution about the rotation axis, and we call it the moment of inertia. And so we have formulas for kinetic energy of translation, 1/2 mv squared, and kinetic energy of rotation, 1/2 I omega squared. So mass becomes moment of inertia, velocity becomes angular velocity. Now, the moment of inertia, you don't have to memorize these, but each shape with each different rotation axis has a different formula for moment of inertia. The problems that we will do will have fairly common shapes. It'll be a sphere, it'll be a ring, it'll be a rod. And so probably it will be one of these formulas, or I would give you a different formula for the moment of inertia of the object. So don't memorize these. Just know where to find this sheet in the PowerPoint, and if it's anything that's not one of these 8 objects, I would give that formula to you specifically. So we use those formulas to calculate a whole series of moments of inertia. And the reason we have to do that is because kinetic energy of rotation is now a factor in the total energy of an object. It could be moving, meaning its center of mass could be moving, and that's its kinetic energy of translation, 1/2 mv squared, and v is the velocity of the center of mass. It can also be rotating, and we have 1/2 I omega squared for that contribution, and then it might also have some potential energy. So all of these 3 different factors contribute to the total energy of an object. So the last thing we did in class was to use the kinetic energy formula for a specific example, the case of the baseball. And so figure out the moment of inertia of the baseball, plug it into the rotational kinetic energy formula, and then we compared that to the translation to see that the rotational energy is not 0, but it's not a large amount compared to the amount of translation. So earlier when we've been thinking about projectile motion problems, we didn't really have to worry about rotation yet. But there are a whole host of problems where rotation is the dominant factor, where it's the most important thing. So the first new thing, the next thing I want to talk about is a related idea to rotational energy, and that is rotational momentum. So just like we have momentum for linear motion, for translational motion, we can have rotational momentum or angular momentum in the case when something is rotating. And that's because when an object is rotating, every little chunk of matter is moving with some velocity, and so it has some momentum to it. And if we add up all of the contributions, that gives us a new quantity, which we call its angular momentum. So I've taken the object that we had looked at before, this shape that we've looked at before, which I think I called like a rock or something. It's just a arbitrary random shape. Imagine it's moving in some direction, and then it could be rotating around. And just to make things a little different here, I moved the center of it down here to illustrate. It doesn't even have to be rotating around its exact center, so it could be lopsided. So I shaded this rock so that it's darker over here and lighter over here, so that its center of mass is actually in this weird location. So that means it's going to be rotating around this center. So that this part's going to go around in a big circle, these parts are going to go around in little circles. But every part of the rock is going to be moving, and because it's moving in two senses, that it's rotating and it's translating, its velocity is the combination of those two motions. So this little chunk of matter is moving off in this direction in space because it's rotating, so it's got some velocity in this direction perpendicular to the radius, but then it's also got this added to it, and when you put those two together you get a net velocity. That would be the actual momentum of this thing. But when we calculate the momentum of the whole rock, it sort of takes into account all of the contributions of the little thing, all the little things, but not the fact that they're rotating around the center. So we need to account for that amount of momentum. Okay. So each little object has an amount of angular momentum that is related to how far it is from the center. So we take the radius that it is from the center and multiply by its actual momentum in the direction perpendicular to its radius, and that's what we call its angular momentum. So this formula right here defines the angular momentum of this little chunk of mass. It's the radius times its mass times this component of the velocity, the component that's perpendicular to the radius. In other words, the component that's tangent to the circle that it's moving on in its rotation. So what we need to do to find this angular momentum for the whole rock is to add up all of the little masses, just like we did for rotational energy. So the work is fairly similar. We sum them all up, Ri, Mi, Vi perpendicular, and recognize that Vi perpendicular is omega times Ri, just like we got before with the rotational energy formula. So that replaces this, and we have it in the formula like this. Put the R's together and realize that omega is the same for all of them, so you can bring it outside, and then we arrive at this quantity again, which we should hopefully recognize as the moment of inertia. So starting here, we're getting the angular momentum. I should say, I'm not sure why we call angular momentum L, but that is the traditional variable for angular momentum. And so we're going to stick with it. So big L refers to angular momentum. I guess it makes sense because we used P for linear momentum, and L for angular momentum makes just as much sense as that. Anyhow, L is now equal to the moment of inertia times the angular velocity. And that's actually a nice relationship because it's just as easy to remember this as it was to remember the rotational kinetic energy formula. And that's because all you need to do is remember that mass becomes moment of inertia, velocity becomes angular velocity. So this is momentum, this is angular momentum. The mass becomes the moment of inertia, or the rotational mass. The velocity becomes the angular velocity. The same relationship we had to translational energy and rotational kinetic energy. So now, why is this an actual useful quantity? Why do we think about angular momentum? Well, let's go to how would you change the angular momentum of an object? Well, you'd have to change how it's rotating or change what its moment of inertia is. you could accomplish this change also by applying a torque. In other words, making it rotate by pushing on it in a certain way. Okay. That's analogous to how you would give something momentum or change something's momentum by pushing on it with a force. So torque corresponds to change in angular momentum, just like force results in change in momentum. Now, if we look at the logical consequence of that, if there's no force, there's no change in momentum, so you have conservation of momentum. Momentum is conserved. If you have no torque, then angular momentum will be conserved, and we have conservation of angular momentum. So if there is no present torque on the system, the angular momentum will stay fixed. It won't change. This explains the demonstration I did last time where the bike wheel stays pointing in the same direction. Right? Why doesn't it tip over? Well, if there's no force to pull it over, the fact that it's spinning around means it has angular momentum. So it requires a force that results in a torque to make it rotate. Otherwise, it is stable. Its angular momentum will be conserved. If you do something like twist it with your arms to flip it over, you are applying a torque. You're changing its angular momentum. But now you and the bike wheel are one system, and so you're applying a torque to the wheel. The wheel must be applying a torque back to you, so you begin spinning the opposite direction. So the way to look at it is that initially I have no angular momentum and the bike wheel has angular momentum. I change the angular momentum of the bike wheel, and now I have to somehow gain angular momentum so that the total stays the same. That's the basic idea of the conservation of angular momentum. And actually, let me, before I go to that problem, so in my example here, I have a certain amount of moment of inertia. And as long as I'm holding the bike wheel in roughly the same way, that moment of inertia is not changing. So what changes is my rotational speed. Okay, so let's see an example of where we use these quantities, and we'll sort of work our way to angular momentum starting from the Earth's moment of inertia, and then we'll start thinking about its rotational properties. So this is really a three-part problem, or it's three examples that are essentially the same, connected to the same problem. And the first one is calculating the Earth's moment of inertia, and the information we have is that the mass is 5.972 times 10 to the 24th kilograms, and it has an average radius of 6,371 kilometers. The other piece of information which is not here, but is hopefully obvious, is that the Earth is a solid sphere. So we want the formula for the solid sphere, and this mass and this radius. So let me escape out of here for a second, flip back to this slide, and if you remember, these are the two spheres. One of them is hollow, one of them is solid. The solid sphere will have a smaller moment of inertia because it has matter closer to the axis of rotation. 2/5 is smaller than 2/3, so this is the solid sphere one. So this is the formula we want. 2/5 mr squared, and this is m, and this is r. So let me slide this over so we can still see the numbers. And let's do the formula. 2/5 m is 5.972 times 10 raised to the power of 24, and then r squared. R squared is 6,371 kilometers. So I need to convert kilometers to meters to be in standard units here, and it doesn't say I have to be in standard units, but I will want it for part B. So then I need to multiply that by 1,000. Okay, and that radius is getting squared, because it's mr squared. Okay, so we get an answer for the moment of inertia of the Earth based on this formula of 9.69, or let's round to two significant digits, we'll keep it 9.7 times 10 to the 37. So let me write that answer down here. 9.7 times 10 raised to the 37. That's the Earth's moment of inertia according to the calculation. Whoops. The actual measured moment of inertia of the Earth is 8 times 10 to the 37 kilograms meters squared. So this is what we got from the formula. This is a little bit smaller. This tells us something about the Earth. So before I say what it is, pause the video, think about it for a minute. What does it tell you about the Earth that the actual moment of inertia is a little bit smaller than what you would get from the formula? Okay. So after you've had a chance to think about it, hopefully what you thought about was the mass distribution of the Earth. How would you make the Earth's mass distribution result in a smaller moment of inertia? Well, you'd have to have more matter located closer to the center. That's how you decrease moment of inertia. You bring matter in towards the center. That tells us that the Earth must be more dense, closer to the center, less dense, further away. And if you know a little bit about geology, you know that's true. Earth has an iron core, and so it is more dense at the center, less dense as you move out. And that's why the actual moment of inertia is a little bit less than what you get just from the formula, assuming that it's, a solid uniform density. So let me put the actual over here, 8.0 times 10 raised to the 37. So this is incorrect. And this, whoops, and this is actual. Moving on to the next question, we're looking at Earth's rotation. The Earth makes one rotation every 23 hours and 56 minutes. We can use that to figure out its angular velocity, and then ultimately we're going to calculate its angular momentum. So angular velocity, radians per second, and we know it makes one rotation every 23 hours and 56 minutes. Now, we could go in a couple of different orders. I know I'm ultimately going to want time in seconds, so let me take 23 hours and 56 minutes and convert it into seconds. Where is my, there we go. So 23 hours and, let's just drag this over. 23 hours and 56 minutes. So 23 hours times, let's see, 60 minutes in an hour times 60 seconds in a minute would be 82,800 seconds, plus 56 minutes times 60 seconds per minute. So we have a total of 86,160 seconds that it takes to make one rotation. One rotation is 2 pi radians, so our angular speed is going to be 2 pi divided by 86,160 seconds. So it's a very small number, 0.0000729 radians per second. Let's do it this way. So what would that be? 7 times 10 raised to the, let me keep another significant, 7.3 times 10 raised to the 1, 2, 3, 4, 5 to the minus 5 radians per second. Okay, next, using the correct moment of inertia, calculate its rotational energy, and then the next part will calculate its angular momentum. So we want rotational energy and then angular momentum. So rotational energy is going to be 1/2 I omega squared. And the I we want to use is the 8 times 10 to the 37. And omega squared, we just found omega is, let me put it in parentheses, 7.3 times 10 raised to the minus 5. And that quantity gets squared. So the rotational energy of the Earth spinning on its axis is 2.1 times 10 raised to the 29. And this would be in joules because I've kept this here in standard units. If you look back to the slide, it's kilograms meter squared, and this is radians per second. So we end up with joules for the answer. All right, and then the last part was the angular momentum. Angular momentum is moment of inertia times, I can just do this, moment of inertia times angular velocity, which I just took this part. Now it's not squared anymore, and there's no 1/2. And so the angular momentum of the Earth spinning on its axis is 5.8 times 10 to the 33. There's no fancy unit for angular momentum that I'm aware of. There wasn't a fancy unit for regular momentum either, like there's a joule for energy. So we just write in what's there, and it's moment of inertia times radians per second. Moment of inertia would be kilograms meters squared for moment of inertia. Radians per second would give you per second. So little weird units there, but that's what it is. Okay. So we have calculated its angular velocity, then its moment of inertia from the previous problem to get rotational energy, and then angular momentum. On to the last part of this three-part problem, the orbit, the actual orbit itself. Okay. Earth makes one circle around the Sun in 365.25 days and an average orbital radius of 149.6 million kilometers. We want to find its velocity and then calculate its translational kinetic energy, compare the rotational kinetic energy to the translational, and then think about the difference between the angular momentum and the linear momentum. All right. So I think I have these answers down so I can delete them. Start fresh. All right, so I want velocity in meters per second. I have the time here in days. So 365.25 days, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So we have this many, 31,557,600 seconds in a year. Now, to get its actual velocity in space, how fast it's moving, we need to know how many meters it goes. So we need the circumference of Earth's orbit. The formula for circumference is 2 pi times the radius, and the radius is 149.6 million kilometers. So let me write the 149.6. Now I need to write million kilometers converted to meters. A million is 10 to the 6th power. Kilo is 10 to the 3rd power. Put them together and you have 10 to the 9th power. So 2 pi times the radius converted to meters gives me 9.4 times 10 to the 11th meters around Earth's orbit. Now we can take this number and divide by this number to get the actual velocity, how fast the Earth is moving through space, 29,786 meters per second. (29,786 meters per second). So that's how fast it's moving through its orbit. calculate Earth's translational kinetic energy. We have its mass from a previous part up here, 5.972 times 10 to the 24. And we'll need that because the formula for kinetic energy is 1/2 times m, 5.972 times 10 to the 24, times velocity squared. And the velocity we just found, 29,786 squared. Oops, I need to put in I think I need to put a multiplication symbol there. Might have done it automatically. All right, so we end up with energy for translation of 2.6 times 10 to the 33. And that would be in joules. Let's see. All right. Now we need to compare the rotational kinetic energy to its translational kinetic energy. So rotational on its axis compared to translation going around the sun. So that's comparing this number to this number which we found earlier. And as I've said before, when we compare things, we take one and divide by the other. At least when we're comparing quantities, you take one and you divide by the other. So the first one is 2.1 times 10 to the 29 joules, and we're dividing that by 2.6 times 10 to the 33 joules, which is 1, 2, 3, 4, 5. So 8 times 10 raised to the minus 5 times the translational. So the rotational is 8 times 10 to the minus 5 times the translational energy. Might help to think of this in the reverse fraction, because this is a number less than 1. It's hard to interpret that. So maybe I should reverse these things. 2.6 times 10 raised to the 33 divide by 2.1 times 10 to the 29. And now I'm getting how many times the rotational is the translational, and it's 12,380. So this answer would be rotational is 8.8 times 10 to the minus 5 times the translational, or translational is 12,381 times the rotational. However we want to look at it is fine. The bottom line is there's much more translational energy in the Earth than there is rotational energy in the Earth. So it's sort of similar to the baseball problem, actually. Okay. Last part here, how does the angular momentum compare to the linear momentum? So now we need to compare those two, linear momentum and angular momentum. So we have calculated the angular momentum here, and to compare it to the linear momentum, we need to calculate the linear momentum. Let's get rid of these. So linear momentum is mass, 5.972 10 to the 24, times velocity, and the velocity was 29,786 meters per second. Okay, so it has a momentum, not angular momentum, but a momentum of 1.8 times 10 to the 29 kilograms meters per second. Now, can we compare this to this? No, because they don't have the same units. But what you can do is realize that the Earth actually has two kinds of angular momentum. It has angular momentum spinning on its axis, And it also has angular momentum moving around in its orbit. And to get that angular momentum, the second one, the angular momentum of its orbit, we just need to multiply by the radius of the orbit. We have how fast it's going times its mass already, and the last step is to multiply that number, this number here, by the radius of the orbit. Okay. So I should have remembered that number. I stupidly deleted it, but it's the circumference of the Earth's orbit, so we can calculate it again. 2 times pi times the radius of the Earth's orbit, which was 149.6 million kilometers. 149.6 times 10 to the 9. Okay, so for the angular momentum of the Earth in its orbit, we get 1.7 times 10 to the 41 kilograms meters squared per second. And that we can compare. So this is how much angular momentum it has spinning on its axis. This is how much angular momentum it has going around in its orbit of the sun, because it's essentially rotating in two senses, the spinning on its axis and the orbiting around the sun. So to compare them, let's do the big divided by the small. 1.67. What did I have? No. 1.7 times 10 to the 41 divided by 5.8 times 10 to the 33, and we find a pretty large number here. So what will this be in scientific notation? 2.9 times 10 to the 3, 4, 5, 6, 7, 10 to the 7 times larger, or times the angular momentum of rotation on its axis. All right, so what would this be? This would be 29 million times bigger. So it actually has 29 million times more angular momentum in its orbit around the sun than it does spinning on its axis. Okay, so but hopefully through this example, you've seen how we've been able to use these formulas to calculate things like moment of inertia, rotational kinetic energy, and angular momentum, and then compare it in different senses to the different aspects of its motion. All right, so that's it for now. Let me know if you have any questions on these examples or the concepts of angular momentum and rotational kinetic energy.